Let's see. Oh, I guess it is. Okay. So I went late in the last one. Okay, let's see where. Okay, so this is kind of where we were at. Let's see if there are. Oh, he's got this extra part here. I guess we should do this. Um, Sometimes I wonder if this is actually as useful as it might seem, but since it's here, we'll talk about it. So actually, you can take a force and move it around as long as you maintain uh, the same force at all locations in the body. For example, what he's done here on the top one is it seems weird. It seems, as you look at it, it seems kind of dumb, but he's taken that force and moved it back here. That's all fine because this is what you feel back here. So what you're thinking about is, what do you feel here? Over here, what do you feel? You have to twist your wrist really hard against this force, and you also have to lift up. So what he's doing is he's taking this force when he's decided he's going to move it over to here. So in other words, this is equivalent to this. So what he's doing is he's making things equal. Now, this step in between is just a logical step, so to speak. And so if you look at it, for example, here's a light, a stoplight. You could move these two forces over to here, and this is what he's done. The resultant force and the force that would be felt by these two moments, D times weight 1 and D2 times weight 2, should be the equivalent moment back there. And so, and he has another one, another section he does. Let's see, one more section. Maybe it's all okay. So then he goes through a further simplification. And I guess this is the situation where sometimes people recognize this right off and some people don't. And if you look at it, this first one right here, this kind of blue square, just so happens, it does not always have to happen, but it just so happens that every one of these forces pass through the same point. Therefore, if you pick this point O, none of these forces produce a moment about it. So that means you can basically sum them up and actually, sum up all the forces. And this drawing is equivalent to that drawing. And I guess, okay, so what he's doing here is he's going in and saying, okay, well, what happens? Okay, give me a second. What happens if, in fact, they don't pass through? Now, all four of these forces do not pass through the same point. So you could do something like, say this, pick this point, and actually this would create a moment about that point, and this one would create a moment about that point. But this one would not, and this one would not. So no matter what you could do, you're going to have to find something like that. So he picks a point, and he says, okay, they don't pass through the same point. But guess what? You can take this, and he's shoved this force. Okay, so what he's doing, he's taking this force. Okay, let's see if I can do this. And he said, okay, I'm going to move it out here. The force is the same. If I move it this way, that's not going to be the same. But if I move it down here such that this distance times this force is actually equal to that moment, then I can put it there. It sounds weird, but there's a place on most... Ooh, that's really strange. Okay. There's a place on most, well, essentially all bodies that you can find that. This one was super easy. This one, not so much. But you can do it. And so he goes about talking about this. And let's, okay, so then he goes in here and he takes the stoplights examples and goes further with them. But let's just pick a problem down in here. Those are the ones that are worked. I'm going to pick one down in here. Because the two last sections are kind of similar. It's this one's kind of adding up to. Here's that one. Okay. So he's got four forces in a weird arrangement here. Very strange. And he says, well, which one do I want to do? Let's see. Replace the load on the frame. Okay, so first of all, okay, this is 21 and 22. I'm sorry, 20 and 21. Replace the load on the frame by a single resultant force. Specify where the line and its actions intersect the vertical line AB. Okay, there's AB. Replace the load on the frame by a single resultant load. Specify the line of action intersection A intersects a horizontal line. Okay, so this is the key. Where is at the end C? That's got to be C. I see A, C B. That's got to be C. I don't see it, but I'm going to assume that's the case. Because he said horizontal line. So, do you see a C? I don't see a C. So, let's go ahead and do that one. To do that, I got to go over here and create a new thing because, let's see, I'll just wonder where it'll be put. That's probably fine. It really doesn't matter where it's at. Okay, so here's the deal. He has given us some guidance that, we'll just stick with. I'm not going to change the coordinates into anything but that. Now, there's 2 or 3 ways to do it. Okay. One is, and I'm going to do this because I'm just going to follow the rules, so to speak. There must have been a red dot over there. So I'm going to call this force 1. Here, I'm going to change color. I'm going to call this one force, okay. Yeah, I hit the escape key for some reason. This one will be force 1. This will be force 2. This will be force 3. This will be force 4. So I'm going to work them down through here. So what I'm going to do is R1 cross F1 and I, J, and a K, and the R is pretty simple. You start here, go up 1, get 1. You know what? Maybe I'll do this. I'll go ahead and list the R's on all these. Okay, so this is force 2. So this is going to be moving up 1 and 2.5. I'll put the forces in there in a second. R3 cross F3. Okay. 3 is this one. So I move up. Okay. Let me get all this stuff off here. I move up here, here, here. That's 2 into the left a half. So I'm moving up. Wait a minute. Sorry, that's 3. This 2.5, another half. That's 3. Moving back to the left a half. And that's that one. So then I'm going to do R4. So it's F4. I'll go back and put the forces in a minute. I, J, K. And then here. Okay. So I still go up 3. This time I go to the left 1.5. Now I'm going to come in and put the forces in it. So I'm going to start with this one, which is, okay, minus 4/5. So we're running back this way. You know what? I think what I'm going to do, I'm going to go ahead. Okay. I'm going to go ahead and put in the, so the 320. So this is 320 moving back this way. 320. And then the other is going to be 240. So minus 320, 240, and 0. Then the next force, which is this one, you're going to go to the right 3/5 of 900. Okay, 3/5 times 900, 540. And then that's to the right. Then it's going down 4/5. Let's see. And that's minus 720. Ooh, these two are easy. This one's going straight up 600. This one's going straight down 400. So what I'm going to do is I'm going to make use of that cross thing in MATLAB, Octave, whatever you want to call it. So I'm going to do cross, and it's 0, 1, 0. That's weird. 1, 0. And I'm crossing it with minus 320, 240, and nothing. Close it out. Uh-oh. I didn't like the fact that I made a mistake. Oh, look at that. Hit the wrong key. 320. So it's 320K. Is that right? Yeah. They're all going to have a K component. They're all, anyway. Let's see. Can I move it? Yeah, let's see. Yeah, I can move it there. Okay, it's not. Okay, so I'm just going to arrow up. So this is 2.5, and it's 540. 540. And then, now y'all have to help me because I'm sitting down, so my brain is not working. Minus 1350. Okay. So what I'm actually, so let me kind of explain what I'm actually doing. I'm actually going to try to find so I've actually got all these things. I'm going to try to find an equivalent moment down here at A, and that's what I'm doing. So And that's all I'm doing. Okay. I'm guessing that's a 600. Here. Okay, this time I'm moving back 3, but I'm also moving backwards minus 0.5. Is that correct? And then I don't have anything here. And I do have something there. 600. Done. Minus 300. And then let's see. Okay. Move it up to here. 4. That's F4. Was that 400 down? Yeah. Okay. So let's go in and put an extra 1 there. And then put a minus 400 here. And so I get 600. Okay. So if you add these, I don't feel like adding them. I'll just let MATLAB do it. 600 plus 320 minus 1350 minus a 300 minus 730. So the total moment about the origin is going to be that. So I'm going to hang on to that for a minute, if you don't mind. And now what I'm going to do, this looks weird. And let me see if this makes sense to you. Since I have all of these together, I simply want to do F1 plus F2 plus F3 plus F4 to get the total value of force. So I'm going to take this number plus that number plus that number plus that number, because that's the forces. So see, 540 minus 320. 540 minus 320 gives me a total of 220. Okay, so it's going to be 220I. And the next thing I'm going to do, here, let's do this too. Let's drag that down to there. The next thing I'm going to do, I'm going to take, oops, that didn't work. I don't like that color anymore. Here, let's do that. So I'm going to take this one. What is this? Oh. I'm going to do this one, that one, and that one. So they all had, not all of them had an X component. These two didn't have an X component, but they all have a Y component. So adding up the blue, or depending on the way you look at it, subtracting the blue, I get 240 minus 720 plus 600 minus 400. 400. That gives you a total of minus 280. So the total force there is that. Oh, that's an 80. Okay, so what you get, let me just get the picture. Copy the picture. Put the picture right here. So what you get is, okay, remember with these moment things, this is X and this is Y. This is a positive. And so if I start looking at this with, so minus 730. So here you go. Oh. There you go. 730. And then what was it? 220 and minus 280. Okay. And just 280. So there you go. So here's your force thing. So you could imagine that. How could you do this? You could say this. Here's the way you could say it. Tell you what. Right to the book. Let's see if I can do this. Oh, wait. What the heck? That's not what I wanted to do. I wanted to do new. And then I wanted to do this. Let's see. I can come up here. What I want to do, get rid of all that. Okay, so I got a thing with no forces on it. So technically, I just sort of put it right here. And then what I'm going to do here, uh-oh, why is it not working? Do this and move that over onto that here. It's mad at me because I need to order, okay, order, send to the back. Okay, and then I got to do this again. Now that's what we're looking at. So the question is, where do I move this force? This force has to remain its current value. Back there. Okay. It has to remain its current value. It has to be this. And what I'm going to do, how do I do this? I'll do it like this. I'll take this, move it out of the way, move it up, move that out of the way for a moment. And then what I'm going to do, I'm going to select the whole thing. I'm going to do a copy. I'm going to put it right next to it. So this, on the right, has to be equivalent to what's on the left. How do I make that happen? And so what I'll do is I'll start moving this force. So I'll move it out to, say, somewhere. Now the key is I can move it up here, or I can just start shoving it to the right. So if I start shoving it to the right, how far, this is like how far do I have to go? You know, and the other thing is, I can shove it anywhere. I can shove it to the right. I can shove it up. There's he wants to know several things. So he wants to know, one is, where would it be equivalent if I shoved it up? Let's do that one first. If I shove it up here, how do I make this thing equal to that thing? Well, first of all, the forces are exactly equal. So it's not a matter of the forces, it's a matter of the moments. So how far did I have to shove this up? I'll call this one D1, because I'm going to do another one that's called D2, so that these two are similar. Well, if you look at the moment over here, it's just 730, and it's 730 that way. So you look up here, and it's 220 times D1. If that's 730, so in other words, this force going down doesn't produce a moment, because it's still going straight through it. The one going to the right, it starts producing a moment. So how far do I have to move it to produce the same thing? Hang on. That is not what I'm looking for. That's what I'm looking for. I'm wanting to take 730 divided by 220, and I have to move it 3.18. Okay. 2. Now, another way I could do it. Okay, this is I'm doing this just to verify. Okay. So I'll copy it again, and I'll put it all right there. And this time, okay, so I've already done this. So I'm just going to leave that one over here and say, yeah, that's good. Oops. Okay. Okay, hello. I'm going to say, that's good. Okay. But this time, I'm going to do this one a little bit differently. Oops. I'm going to come back. I'm going to say, I want to know how far to the right I have to move it. How far to the right do I have to move it? That was D1, so I'll call this D2. So this time, the moment has to be the same. 730 is equal to D2, but this force is 280. 280. Let me get rid of that circle. So remember, this is the 220, and that's the 280. So that's why I multiplied that 220 up here by the D1 to give me this moment. Now I multiply the 280 because I'm moving it straight to the right, and I move it straight to the right. So that means D2 is equal to, if I can find that, 730 by 280. Oops. 2.61, 2.6071. Okay, so this is interesting. So now, let's do, what's that called? Transmissibility. Here, I don't know. Here, green. We'll do green. So if I do this, it should do that. And this is transmissibility here. So let's look at this triangle now. Oh, shoot. Okay, go away. Okay, so here's a triangle. I'm doing a check here. So I'm going to look at this triangle, and this. I'm going to look at that part of the triangle. And I'm going to say, if this is 2.6071, what's the other? Okay, first of all, the ratio has to be such that, and actually I should be able to directly figure this out. But if for every, okay, so if I go back to the original, no, I think I could do it that way. Let's do it this way. Here's what I'm going to do. I'm going to find the angle here. I'm going to do something I don't like to do just because, well, why not? Okay, wait. I don't want to. Here's a good color. So I'm going to say, what is this angle right here? And isn't that angle the same as that angle? And then I'm going to start working the problem. I don't like to go to trig first and then come back out of trig, especially when I have ratios. But I'm going to do it here because, as you can see, I'm sitting on my, you know what, I'm not walking around. So the blood is not going in my brain. So I'm going to do it this way. So, I don't know. So this whole thing, I don't even know the value of this thing. But what I'll do here, I'll go down here and I'll say, if I've got a triangle that is like so, and it's 220 and 280, what's that? Well, we'll just call it theta. So let's say cosine theta is equal to whatever that length is. We'll say cosine's 220 over that length. Well, that length is 220 squared plus 280 squared. Hey, you know what? If I use another pen, I could make that photomath to it. Cosine theta. So the question is, okay, this will be interesting. I think it's, what is it on there? A cosine? Arc cosine. 220 divided by 220 squared plus 280 squared. Let's see if it'll do that. Guess the pollen is picking up. Let's see if it recognizes a cosine. It does. It recognizes it. 51.84. So if that's 51, let's go back to this. If this is 51.84, then what's this distance? Well, I should have gone to tangent to begin with. But the tangent of 51.84 is equal to whatever that is. I'll call it h in here because I'm not going to assume that it's the same distance. H over, what the heck was that? 2.6071. 2.6071. So here, I'll just do this on octave here. We're going to have to do tangent degree of 51.84 times 2.6071, 3.3178. Okay, 3.31, which is the value. So that proves, so what I just proved is transmissibility works. The next thing is, where does it hit the top here? In other words, you can do it off of either one of these, but it doesn't really matter. So in other words, the next thing I need to do is I need to do this. Here's my new triangle. This time I know that's 3. I still know this is 51.84. Now I want to know, actually, I want to know this distance, but the tangent's going to find that distance. So what this becomes is, and I go away. The tangent, okay, here we go. Here, I'll do back to here. So that way I can write really small. Tangent of 51.84 is equal to 3 over this distance right here. dA, I don't know what to call it. So dA is equal to 3 over tangent of 51.84. I'll just use MATLAB to do that because I've already got the tangent in there. 3 divided by that gives me 2.3574. 2.3574 dA. That has to be, ooh, that's not right. There's something wrong there. What did I do wrong? Okay. Oh, you know what? That is right. The reason that's right is because this, okay, so the angle was such that, okay, so let me draw this to scale, and this actually goes up to here, and here, this goes up here, and now this is the, so in fact it's above it. So that means it's to the right. Where did my number go? So 2.3 is where it crossed. So that means it's to the right. What's the difference between those two? 2.6 minus 2.3. 2.6071 minus 2.3. 574. 0.249. That means, if I can pick, oh, orange. I haven't used that right there. That's not orange, that's red. So that's the 2.49. So that's where it actually crosses right there. So I hope this kind of made sense. Oh man, I should have taken some Claritin or Zyrtec or something. Whoa. So if you look at that, that's all these things are, is taking the thing, taking the forces, whatever they happen to be, locating them wherever he asks you to. In this case, like, replace the force acting along the post by a resultant force. This part would a line of action intersects post AB. So you're going to find some sort of equivalent. So the thing about this, okay, let's think about it like this. Go back to the original value or the picture. Okay, here's your picture. Let it come up. So, yeah, you moved it about somewhere, and then you found this, right? So here's your force. But here's the unique thing here, and that is that force can be anywhere here. So you can take this force and literally move it anywhere along that line. So it might cross right here, might cross right here, but they're both equivalent because you're moving it along the line of transmissibility. So it's fine wherever you put it. So that's what he's doing here. When this problem, he first wanted to know if I translate that force, I can translate it to this point right here, which is what I did. I can translate it here, but guess what? I can do something else very strange here. I can take this force and transmit it to right there, because that's the line of action it takes. And so any one of those is fine. So I think that's the end of this chapter. Let's see if there's anything. It's just a bunch of problems. Get posted. What is this? Oh, this is a. Okay, so I do need to do 4.9. So let me talk about it for a minute, and then we'll kind of say we're done. So 4.9 is the last part of here. So 4.9 is like setting up this concept. Let's imagine you're building a house and you've got a structure up here, and somebody's going to start laying bricks. So they start laying bricks. Okay, and then the beauty of this thing is I can do this, and I can say copy and paste. So they start laying bricks all along here, and then it's interesting that it puts it right down at the same level. So he starts laying bricks, but he stops there. Then he starts laying them in a weird pattern. And so of course you can't lay them in midair. So what he's started to do is do something really bizarre like this. So let's say he did something like that. Now, let's just say maybe a beam. I mean, all the bricks weigh the same. So actually, if you just wanted to do a diagram, it would kind of look like this. Well, it would kind of look like this. So in other words, you'd have your beam, and the load would kind of look like this. So here's your load. Now, of course, it's actually more along, it's an exact duplicate of this. So if you're looking at it, this is actually the diagram of it. But this means basically you could have a function of x if you actually put that as x. This is what he starts talking about. He starts talking about, well, send an x out this way, and this is now the weight. Now, it is a physical coordinate of y as well, and the y and the weight are the same if you start considering like the brick weighs so much per height, So you can start seeing this similarity. So the height of this funny curve or surface across the top here is associated where, like, say you had a lot of really tiny bricks and you laid them out here, you could actually get a very nice curve like that. Not sure you really want to pay the labor to do that, but you could. And then you get some weight as a function of x. So what do you do then? If you want to know the equivalent weight, well, what you really want to know is, of course, how much it weighs. So the weight that he has here is going to be like in pounds per running foot. The running foot being this way, say foot. It could be meters. So it could be newtons per meter running out there to the right. So where is this load acting at? Well, if you put your finger right here, if you were strong enough, and you lifted straight up, you basically, that would be compensating for that load. So it turns out it's at the C or centroid of that area. So how does he go about doing that? He says, okay, here's my force. I'm going to integrate the weight over the distance. So when he says the area, he's talking about the area of, if you look at it from the side, it's the area of the profile. And so then it's like, hey, if you're integrating the area, then that's just simply the area. So, for example, if you had it lined up, so it was a perfect uniform thing here, and say you had, 20 pounds per running foot, and you had 10 feet. Oops. Anyway. So 10 feet times 20 is 200. So it's a total of the area. So it's the area under here. It just so happens sometimes, not often, but sometimes it's not a square. It's like a function. How do you find the location? Well, what you do is you go in and you say, now that I've found the load, in our case back there it was say 200, I want to find the distance out there to it, to where if I put my finger underneath it, I would balance it. So what do? You take the load itself, this, and you take a little moment arm out there. So you do like that, and that doesn't count anymore. And so what you get is x times this, or x times the area, and it turns out that that's what they call the centroid, or the center of the mass of all the bricks up there. So if you were able to jack up straight under there, you could pick up the beam and balance it if you were really good at finding that location. And so essentially, and here's some bricks. So there you go. So there's some bricks the guy, there it is. The bricks the guy laid out. And of course he stacked them in like a triangle. So it's like a triangular load on those wood parts there. Whoa, it jumped there for a minute. I don't know what's happening. So you can have an equation. You can go through and integrate it, find the actual force by doing the integration of whatever that was, 60. So there's the weight per running foot. There it is. You integrate it. Then you put the x in there, and you do the 60x squared, same with the x in front of it. You carry under here the 160 that you picked up from here, and then you get the location of the load. So I think next time I'll spend some time to focus here. I want to focus on this problem because it's kind of unique. And I guess I'll focus on this one, but I may just come up with them instead of numerical values there. I may come up with, I may do them on the other sheet and make it kind of generic. And then it's just basically going through a bunch of problems. That's all it is. Most of them, looks like most of them are linear. I don't see, to this point, I don't see anything with an equation yet. These are all linear. Let's see if I do. There'll probably be one, at least one in here that has an equation. There's one with an equation. There's another one with an equation. And another, and another. No, he puts another here. Okay, that's it. So it looks like right near the end, everything is near the end. And these are review problems, so there, we're completed with chapter 4. Yeah, that's chapter 4. Chapter 5, we're going to start looking at free body diagrams for two-dimensional things. And then we'll go on to three-dimensional things. So I'll let you go like 4 minutes early if you're fine with that. I have to cut fluids short in order to go get some Claritin or something.